All right, AP Chem, if you remember when we did thermochemistry, we're going to remember that we learned a general reaction diagram when we were in thermochem, and now we're going to add a little bit more specifics to it. Because now we're also going to learn that certain chemical reactions take place in more than one step. So how can we deduce the number of steps in the mechanism? By looking at the potential energy diagram. You're going to see that there's a certain amount of curves in there. How do we tell if it's exothermic or endothermic? Well, you're going to look at the energy in the beginning and then the energy at the end. Which one's more? That'll tell you whether it absorbed energy or released energy. And which step in the mechanism is the rate determining step? Well, that's going to be determined by which one of them has a taller curve. So let's go through. This is the simplest example. This is a one-step reaction. So the potential energy of the reactants is here at 100 kilojoules. This assignment is a good one because we really need to get better at learning how to read graphs. Graphs are super helpful, and they're going to be super important as you go further on in science. So I'm going to put a point right here for the potential energy of the reactants. And then the potential energy of the products over here is 600. And let's go over the different parts. The activation energy is how much energy do I need to add additionally to the reactants in order to get the reaction to happen. The activated complex, it says, is up here at 750, like such. Let's draw this curve and see if we can interpret some information. This is what this reaction graph is going to look like. So the activated complex is up here. I would label this as the activated complex. And now we can calculate the change in energy for the reaction, which is delta H. That is remember, H is enthalpy. So the enthalpy of the reaction is the difference between the energy of the reactants and the energy of the products. So in this case, the reactants are 100, products are 600. Therefore, the change in energy for the reaction is going to be the difference between those. The activation energy, which is E sub A, is going to be this quantity here, which is the difference between the potential energy of the reactants and the energy of the activated complex. So it's going to be 750 minus 100. So my activation energy is 650 kilojoules. That's how much energy I would need to add to my reactants in order to get them to react and turn into products. All right, let's do reaction number 2 together. Do the same thing. The potential energy of the reactants is 350. This time they did not give us the potential energy of the products. The potential energy of the intermediates is going to be, I can see that this is a two-step problem because of that. So the intermediates are going to be right here. And then it says the activated complex 2, so that's going to be my second. This is going to have two parts of the curve, is 700 here. And the initial activation energy for the first step is 400. So I'm going to take the 350, add 400 to 750, and that's going to be my energy of my activated complex 1. Like such. So this is the activated complex number 1. This is the activated complex number 2. So it says here the change in enthalpy is negative 200 for the second part of the reaction. So the middle is 500, and then the end will be 200 less than that. So minus 200 down here at 300. So the potential energy of our products is going to be 300 kilojoules. Now we've got everything we need. Let me just draw the curve here. This is a two-step problem. This one is exothermic because the potential energy of the reactants is 350, the potential energy of the products is 300. So overall energy was released from this reaction, so it is exothermic. The overall change is minus 50. Remember that we only use minus signs in order to indicate that energy is either being released or absorbed. So now let's go. In the change in energy for this first step, we went from 350 to 500. So that is plus 150. And the activation energy from this for the second step, needed to go from 500 to 700. So it is plus 200 kilojoules. So these guys right here are the intermediates. This is activation energy 1. This, from here to here, is activation energy 2. Now, when it comes to the rate determining step, the rate determining step is going to be the step that has the higher activation energy. So that's going to be step 1. Rate determining step is the slow step. A 3-step one now. Potential energy of the reactants, 200 kilojoules. Potential energy of the product, 550. So I can right now, if I want to, the overall delta H is 200 minus 550. So it is an endothermic process, and it is plus 350. Change in enthalpy for the first step is going to be minus 100. So we're going to go down here. Okay, so potential energy of the first intermediate would be 100. Potential energy of the second intermediate is going to be 400, like this. Change in energy. The activated complex 1 is 500. Activated complex 2 is 450. Activation energy 3 is going to be 250, so it's going to be 400 plus 250, or 650. Now this is going to allow us to connect all the dots. Like such. So activation energy 1 is 300. Activation energy 2 is 100 to 450, so 350. So therefore, my slow step is going to be the one with the highest activation energy. Change in energy for the first step is minus 100. Change in energy for the second step would be 300, because we've got 100 to 400. And then the next one is plus 400 to 550 plus 150. And then activated complex 3 would be 650. So the slowest step is going to be the rate determining step with the highest activation energy. The fastest step is going to be the lowest activation energy, so that's going to be our third step here. So our second step is rate determining, and our third step is the fastest. I just want you guys to understand what we mean by activated complexes, activation energy, how many steps a reaction has, and how to determine the change in energy for that. Anybody have any questions? Does it seem like it makes sense? This is our introduction to 2- and 3-step problems that we're going to add to our 1-step problem. And we're going to start thinking about concepts such as activation energy, activated complexes, and multi-step problems and how they determine which is the rate determining step, which is the fastest step, based on how much activation energy that they have.